Hello and welcome back, everybody. Today in calculus, we will be talking about integration using partial fractions. So this is something that was from Algebra 2, so, at least a couple of years ago for most of you guys. So let's go ahead and kind of review what partial fraction is, and then afterward, we can go ahead and jump into a problem where you're going to see in calculus. So this, again, is something from a couple of years ago. What I want to do is I want to take this expression right here, 2 divided by x squared minus 1, and change this into a partial fraction. And by partial fraction, what I mean is that this guy over here, this is equivalent to something of the following. Notice that the denominator has an x squared minus 1, which can be factored into x plus 1 multiplied by x minus 1. So what that means is when I'm looking at as a partial fraction, I'm kind of like working backwards. What I want to do is I want to take this expression and break it into where I have two fractions, the sum of two fractions, where their denominators are going to be those individual factors that you see. So that is to say, this guy right here can break into the following. One fraction where x minus 1 is a denominator, and then the other fraction where x plus 1 is the denominator. So something like that. Now the numerator, we don't know what the coefficients are, so we're going to go ahead and put those as a and b, and we're going to go ahead and solve for those in this case then. So that's where I'm coming up with the following then. All right, so now what I'll do is in order to solve for a and b, what I'm going to do is I'm going to take this equation over here, and I'm going to multiply by x squared minus 1, which is the denominator, because I want to get rid of all of those small little fractions if possible. So if I do so, we're going to get strictly 2 on the left-hand side. And on the right-hand side, we have a multiplied by x minus 1, and then plus b multiplied by x plus 1. And focus here, I want to solve for what a and b are supposed to be equal to. Now what we can do is we can go ahead and solve for it using one of two methods. Either A, we can go ahead and maybe do a substitution, or B, we can do it by using a system of equation. So here, I think the easiest way is to actually do a substitution. And here's what I'm going to do. I'm going to go ahead and say let x equal to 1 in this equation. Now, in the original equation, we obviously cannot do that because x is equal to 1 in the denominator would give me something that's undefined. But by changing it into this form, we can go ahead and allow x equals to 1 then. So if I do so, we're going to get then the equation is going to say 2 is equal to, well, this part over here, that's going to give you a multiplied by 0, so that vanishes out, plus b multiplied by 2, because 1 plus 1 is equal to 2. So this then allows me to solve for what b is equal to, which means that 2 is equal to b times 2, so therefore b is equal to 1. Now, similarly, I'm going to go ahead and let x equal to negative 1, because then I can let this factor over here vanish out also. So in my equation, it's now going to say 2 is equal to a multiplied by negative 1 minus 1, and then plus b multiplied by 0. So to solve for that, we have now 2 is equal to negative 2a. So that means that a is equal to negative 1. So then my conclusion is the following. The factor, not the factor, but the expression of 2 divided by x squared minus 1, I can break that into the partial fraction of the following. Negative 1 over x plus 1, and then plus 1 over x minus 1. Now, that is going to be your partial fraction, like how it's supposed to work out. If you want to, we can go ahead and multiply these guys back and then show that you're going to get this as a result, but we're just going to go ahead and bypass that for the time being. If you're wondering why is it that we need to do that, well, now let's go ahead and think of it from a calculus perspective. Let's say that I want to find the antiderivative of 2 divided by x squared minus 1 dx. Now, according to what we've learned so far, we only have used substitution and maybe some other trig identities that we can possibly use in this case. But now that we have partial fraction in our tools, that would make this problem a lot easier. Because according to what we just did over there, if we were to apply partial fraction in this, we can say that this is going to be equal to the integral of 2 divided by x plus 1 multiplied by x minus 1 and then dx. Now, from the example above, what then that becomes is the following. As we said, it's going to be -1 divided by x plus 1, and then we have plus 1 over x minus 1. And look at what we have now, something that's a lot easier to integrate. Well, now we can go ahead and take the antiderivative of each one of these, and then that'll be our answer. So the first part, the antiderivative, is going to be negative ln of absolute value of x plus 1, and then plus ln of absolute value of x minus 1, and then it's going to be plus c. So that you can go ahead and leave that as an answer. But here I want to go ahead and show you kind of like a small little special trick just to make this a little bit more compact, because this is another variation that you might see. Now, instead of just leaving the answer like this, what we're going to do is I'm going to go ahead and say that that constant, let's not write it as c, but instead let's write it as ln of c. And the reason for that is, if you notice, every single term contains an ln, and that means that we can actually use the property of logarithm in order to clean this up. This will then be equal to the ln of absolute value c multiplied by x minus 1, because that is the plus part, so it goes in the numerator, divided by x plus 1 on the bottom, because that's going to be in the denominator. Sorry, x minus 1 on the top then. So what will happen is sometimes you might see this as the back of the book as an answer, and you didn't do anything wrong, but it's just, they made it a little bit more, I guess, more condensed for the answer by using this ln of c trick over here versus like just say plus c then, okay? But there you go. That's how partial fraction actually works out. So let's go ahead and take another example of this. But before we do that, notice I wrote something down here. This partial fraction trick over here, there is a restriction for it. Okay, so this partial fraction trick says the following over here. Partial fractions only works if the numerator is a lower degree polynomial than the denominator. So if you look at your rational expression over here, you'll notice that the 2 over here is a lower degree polynomial than the x squared minus 1 over here. Meaning that if I have something like, say, the integral from the integral of x to the 4th divided by x minus 1 dx, then we would not be able to use x to the 4th divided by x squared minus 1 dx, then we would not be able to use a partial fraction trick as we just did over here, okay? But it's not to say that we can't solve for it. We'll get to that in just a little bit, okay? All right, so let's go ahead and erase this guy over here, and let's go to look at another example of this partial fraction thing. Example number 2. This time we have the integral of 8x plus 12 divided by x squared plus 2x minus 3. So first, what I'm going to do is I'm going to go ahead and rewrite this, so then that way we can see the factors in the denominator, so we can set up our partial fractions. The denominator, that is going to be x plus 3 multiplied by x minus 1, so that should give me that on the bottom. Whereas the numerator is going to be the same thing. So my setup is going to be the following then. 8x plus 12 divided by x plus 3 multiplied by x minus 1, that is going to be equal to a divided by x plus 3, that's my first factor, right? Plus b divided by x minus 1, and that's going to be my second factor. So there it is, splitting it into 2 parts. So there's our partial fractions. And by the way, if you have, like, say, 3 factors, then that means you're going to have 3 partial fractions, and 4 factor, 4 partial fractions, and so on and so on and so on. Okay. Okay. So now we'll go ahead and try to solve for a and b. And just like last time, what we'll do is we'll take all of this and multiply by the denominator, which is x plus 3 multiplied by x minus 1. So if you do that, we get 8x plus 12 is equal to a multiplied by x minus 1 plus b multiplied by x plus 3. And it's very important that you don't actually multiply out the right-hand side, because that actually makes things more complex. So here, let's go ahead and solve for x by substitution. So we're going to go ahead and say let x equal to, and the value of x that you should always try to choose would be the factors, the zeros, the values of x that will give you the zeros as a factor on the right-hand side. So for example, let x equals to 1. So then on the left-hand side, if I plug in 1 into the equation over here, we're going to get 8 plus 12 is equal to a times 0, which is going to be gone, plus b multiplied by 1 plus 3. So if we clean that up, we get 20 is equal to 4b. So that means that b is equal to 5. So hopefully that's simple enough. Now we're going to go ahead and let x equal to -3 to get rid of that other part. So if I do so, we are going to get -3 multiplied by 8, so that's -24, and then plus 12 is equal to a multiplied by -3 minus 1 plus b multiplied by 0. So clean that up a little bit more. -12 is equal to -a times -4. So therefore, a is equal to 3. So there it is. My partial fraction says that the integral of 8x plus 12 divided by x plus 3 multiplied by x minus 1 dx, that is equal to the integral from, the integral of a, which is going to be 3 divided by x plus 3. And then we have plus 5 divided by x minus 1, and then dx. Those two we can easily take the antiderivative of. So that is going to be the 3 multiplied by the ln of absolute value of x plus 3, plus 5 multiplied by the ln of absolute value of x minus 1. And we're going to go ahead and say plus ln of c just like last time. So take all this guy right here and combine it into one single ln form. My final answer that you might see in the back of the book would be the following. ln of absolute value of c multiplied by x plus 3 raised to the third power, because the 3 can go in as an exponent. And then multiplied by x minus 1 raised to the fifth power, because the 5 can also go inside as an exponent. So right there, that is going to be my final form of the answer then. Now let's look at this last example. What happens if you have x cubed x cubed divided by x minus 1, where your numerator is going to be a polynomial that is greater than the denominator? Well, if that happens, we can do something to make this a little bit easier for us. If it's the case where the exponent in the numerator is greater than or equal to the exponent in the denominator, which is what we have in this case, you can use long division or some sort of cheap algebra trick to divide through first, so then that way we can set up our maybe partial fractions. So over here, you can see on the right-hand side, what I did was I showed the long division. I took x cubed and divided by x minus 1. So you can kind of follow through. So you can see what we have is that when we divide through, you get x squared plus x plus 1, and then plus 1 over x plus 1, because it's supposed to be the residual part, which is the 1 divided by what you're dividing through, which is x minus 1, which you can see is very easy to integrate. So that's the small little trick that you can do to make this a little bit easier. Now, the cheap trick in algebra, which doesn't work all the time, but it does once in a while to make our lives a little bit easier, is look at our equation over here. Look at our expression. You'll notice that we have x cubed on top, and then we have x minus 1 on the bottom. So what I'm going to do is, why don't I go ahead and say minus 1 and then plus 1 on the top? Because I'm noticing what's happening is that if I focus on the first two part, x cubed minus 1, that is something called a difference of cube, which is divisible by the x minus 1 that I have on the bottom. So here, let me just kind of write it out so you can see it. X cubed minus 1 divided by x minus 1, and then plus 1 over x minus 1 dx. Now, according to difference of cube, that first part will become x minus 1. That's one of the factor. The other factor is x squared plus x plus 1, and then all divided by x minus 1 still. And then plus 1 over x minus 1 dx. Okay, so you can see how the x minus 1 cancels each other out. And now we're left with x squared plus x plus 1, and then plus 1 over x minus 1 dx. And hey, look what you have. It's exactly the same thing as what I did when I did long division. So, you take whichever works best for you to understand, and then just apply it. And now we're going to go ahead and take the antiderivative, and that's going to be our answer then. So fortunately, we don't have to do any kind of partial fraction in this case, but you can see how this works out, because when you divide through, sometimes you'll have a remainder that will force you to use partial fraction, and that's where you have to use what's above. So my final answer over here is x cubed times 1/3 plus 1/2 x squared, and then plus x plus the ln of absolute value of x minus 1, and then plus c. Unfortunately, in this case, we don't have to worry about plus ln of c, because there's nothing that we can combine. There's no ln in every single term, so we'll just go ahead and leave it as a constant. But there you go. That is going to be our final answer then. Okay. All right, well, thank you so much. This is the part one of partial fractions. Next time, we'll look at the more advanced and special rules of partial fraction. I will see you next time. Have a good one. Bye.